Hey there, math fans. I'm Dr. Andy All just going to talk about the Taylor series concept, how I would explain it to a friend if I just wanted to explain what this thing was all about. And then I'll give a little bit of history. I started to dig into the history. The history of math is so much. I'm spending too much time on it. So I'm going to stop, tell you what I've discovered in my little bit of research that was on top of things I already knew. And then I'm going to focus on what I do know, which is the Taylor series concept. And then I'm going to move on to those Taylor series applications that I really want to get to. So I'm going to try to bail myself out of the history. Now, an interesting thing I've been doing as I've been reading so much about this history is I started to make my own timeline. So this is the beginnings of my own timeline. I'm going to add to it. This is just for me. If there's major events I'm missing, I know I'm missing major events. I just am grabbing a few things. So in a previous video, I talked about polynomials as a foundational piece of mathematics. I talked about how in the 1500s, someone solved the cubic and at the same time solved the quintic. And the big thing was prove that you can't solve beyond that in terms of radicals. So we can't have the same methods. And that's Cardano's formula for the cubic and Ferrari's formula for the quintic, but they work together. And there's an unusual history to all of that because in a way, Cardano, he got the information from someone else, but then contributed his own, so it's complicated. At that same time, we got complex numbers. So there's a huge history in polynomials, the fact that they're relatively nice to compute. They naturally arise from things we study in math. So it makes sense we might want to write things in terms of polynomials, especially as we get more and more complicated functions. Now, just grabbed a few history along the way. Around that same time, many things were happening. Math dates back further than this, and there's definitely history of math and, other cultures. This is kind of the European focus version. Some of the writings as I was reading from some other cultures just didn't survive, so it's hard to know how much was known in India and China and some other places, as there is evidence that they had some things that were more advanced in certain areas. So it's just that's, like I said, I could spend forever trying to read up on this, and that probably is not what anyone wants to know. Okay, anyways, logarithm tables came up here. People had already been studying, things like logarithms and the symbol e, but this is really where things started. And right here with Descartes, I think I'm saying it wrong, put together this idea of we can visualize algebra, we can graph a line, we can graph a parabola, we can talk about these things. And then Fermat had some of the beginning ideas of differential calculus. So you can see a really jumping off point in the 1600s. It's interesting to look back at this. And all of this, right before that was this big question of what can we do with polynomials? Then lots of things happen. As I sort of I'm going to grab interesting formulas, but this is for another day. There were several books about the infinite. And it was sort of right based on all of this algebra, this geometry, putting things together, that Newton was working on this fundamental theorem of calculus, this connection between derivatives and antiderivatives in a careful way. And at that same time, Newton was already thinking about it as well. But Gregory, I think it's James Gregory, this is just me reading, some of this, like I said, I knew at one point. I'm rereading some things. Gave Taylor series for some functions. And around that same time, Leibniz was studying calculus. There was a big debate about who discovered it first. At the time, these things were heated debates. Anyways, Brooke Taylor was an English mathematician, so he was in the Newton school, so to speak. And it was interesting that in 1712, they had a committee to try to figure out who invented calculus. And he was on that committee. So anyways, won't go into that history. I did find this stamp online from the Netherlands, it looks like, of Brooke Taylor. So Brooke Taylor, unlike some things in the history of math where maybe the person who it's named after isn't the one who contributed the most to it. It does appear that Brooke Taylor contributed a lot to Taylor's series in the fact that he gave a general treatment. Yes, it had been discussed. It appears Gregory did not, what I read was, didn't publish some of his work because he thought Newton had already done it, even though he had actually done a dramatic, taken it much further. So anyways, there's interesting history here. The bristochrome problem is a really interesting one, but that's, again, all for another day. So then in 1712, this Brooke Taylor, who was a mathematician that did lots of different things, sounds like had some troubles in his life, lost a wife and a child, and then it appears the writings I read were that did a lot of great things in mathematics in many different areas, and probably would have done more if his life had not given him so many stumbling blocks along the way. He wrote a book about Taylor series. It was in there a discussion of Taylor series, a full treatment. So that's why it's named after him. So it's appropriately named. Maclaurin studied a special case when this A is 0. So a lot of students hear this Maclaurin series, but really we typically call it Taylor series. Then things really take off. Euler came along and pushed things much further when it comes to infinite series, used Taylor series to his advantage in many ways, and also talked about other types of series. And then Gauss came along in the 1800s, and there's plenty more history to come after that. So that's a little bit of background. You can see that, at the end of the 1600s, a lot of the questions about polynomials were sort of being answered and leading to bigger questions in mathematics. And then you can see this connection between geometry and algebra that's leading to this calculus, this study of, the shapes things will form. As soon as you start graphing things, you might want to know where the bumps are. If you want to know where the bumps are, then you're going to lead yourself to calculus. So when you look at it historically, this is long spans of time, but you can kind of see this development. Okay. Then how do we study things? How do we even think about what e to the x is? E to the x is a weird function when you first see it. E is this number, 2.71828182. Those are the digits I know. And that's weird that I know that many digits, but it has a fairly easy to remember pattern because the first 4 digits and the next 4 digits look very similar. That's how I remember those digits. I don't really have a good memory for things like that. This number arises, and this is why I like having this time here, from around this time. One of the Bernoullis, I think it was studying compound interest, and this came up. This number naturally came up. And then we realized it also plays a nice role in calculus. Okay. But it's terrible to compute. If you had to do e to the third, how are you going to compute that? 2.71828182 to the third. Yeah, you could do it in digits, but it's going to be kind of bad. What if you're raising it to the 3.1 power? What are we going to do then? Okay, so the question is, what can we do? How can we estimate it? What can we work with? Can we turn it into a polynomial and just work with a polynomial instead? Can we think of it as a polynomial? That leads to these natural questions. All right, so now I'm going to talk about the concept. And I'm going to pull up the e to the x graph here for the rest of this. And for this moment, we're going to talk about 0. And when I teach calculus, I tell students at the end of a calculus course, you should be able to think about that the original function tells you the height. And I'm surprised sometimes how often students don't know that. Like I'll label a graph and say, okay, if I give you this x, what's the height? And they don't realize they can just plug into the function because that's what the function is. So I'm going to move this out of the way, our history away for a second. That's how history vanishes. So my question is, if you plug in 0, what is the height? And you can see it. I'll draw it here in a second. Let's go to 0. Now you can't see what I'm doing, but I'm going to show you. So here's this function. There's 0. Let's plug it in. So what is the height? I can't quite see. Oh, there it is. Ah, we can't see the difference. I didn't label it. That's all right. So that little dot, what is it? Maybe I'll add a dot in here. Apologies. So we're going to do... So what is the height of that little dot there? Well, it's 1. It's e to the 0. So the height is e to the 0. If we wanted to construct a polynomial there, we might say, well, I want the height to be the same. So down the page, I have a polynomial. I'm going to start constructing it. This is exactly how I think about. I think of it, a polynomial, as a clothesline for us to hang values of the function. So what we're going to do is we're going to put, I'm stealing that from one of my professors, Professor Matt Huddleston, I think is the one who said that from WSU. But we're going to put a 1 right here. And notice right away, I'm starting to build something. Let's call this g of x. And let's kind of take account of what I've done so far. So right now, if I plug in a 0, even though I don't even know what these other coefficients are, I'm going to get that they match at 0. So the height of the function at 0, and I'll put a few notes here. And this is the concept of why this works. We can talk about some of the subtleties of how can we be certain it's going to 0, but these are the same. And that's going to be our governing principle, is I'm going to construct a polynomial that has the same height. Okay, I've done it. I would like it to also have the same slope. Well, what's the derivative? Now this one, you have to know some derivatives, but the derivative is e to the x. And I'm choosing one that has nice derivatives, but just to show you the idea. And this is enough to get the idea. So that's the slope. If you're a calculus student, you really need to know that the derivative tells you the slope and the function tells you the height, and that together you can answer lots of questions. So I really would like g prime of 0 to be 1. We need to make that happen. So natural question is then, what should we put here to make that happen? And we're going to start constructing. So I'm going to get rid of these for a second, because well, you might say, well, how am I going to do that? Because every time I change it. But let's just keep going, and let's put a 1 here times x. Let's graph that. So I'm going to graph that. It's a line. It's the tangent line. And here it is. We say it's an approximation of the graph if you're near 0. You can see that they're kind of close together. If you get further away, we say there's an error between them. And the error gets worse the further you go. That red line is the error. It's the difference between them. But while we're doing this, let's compute the derivative. So what is g prime of x? Make sure you can see that here. I'm going to zoom out just a little bit. Apologies. Bear with me here. Oh, I tried to make myself vanish. That probably would have been the best for everybody. I'm going to do one more thing here. Okay. We can still see that stamp a little bit. Now, anyways, if we take the derivative, what happens? You get 1. And they do match up. So we're good so far. But the derivative only tells you the slope. It doesn't tell you how the graph curves. And this is the clever idea. We'd say, well, some of our nicest functions, some of our simplest functions are polynomials. How could I construct a polynomial that curves without messing up what I've already built? So this is the challenge now. I would like to add something on here to not mess up the value before, but to match up with the second derivative. Okay, let's do it. Second derivative is this. I'm just going to call this concavity, but it's how the slope changes is what it represents. Okay, so it's the second derivative at 0. E to the 0, it's 1. And our goal is to make the second derivative of the polynomial match up. It turns out that works really well to get your graph to be the same. So anyways, if I just put a 1 here, you will see that it doesn't work. And that's the interesting part here. You say, well, it looks like we should just keep putting 1s. What do I mean by it doesn't work? Well, let's check. The first derivative would be 0 plus 1 plus 2x. The second derivative would be 0 plus 0 plus 2. So the second derivative is 2, and they don't match up. We've failed. This is what I do in class. I tell students, why did we fail? And we try to reverse engineer this. And this is where you understand where the formula comes from. It specifically has to do with the fact that we're approximating with polynomials. And so I have students track back, well, where did that 2 come from? It came from that exponent. That's the problem with polynomials, is they have these exponents. Well, shoot. We go, is there anything we can do to get rid of that 2 and so that there's a 1 down here? So then we have this goal. The goal is for this number to be a 1. But in order for this number to be a 1, this number needs to be a 1. But in order for that number to be a 1, this number has to be a half. And there's the beginning of our formula. So in order for this to be a 1, in order for our concavity to match up, you have to have the following. So let's kind of summarize where we're at. Kind of put it in solid. We go 1 plus x plus 1/2 x squared. And now you can see why that 1/2 is there, because the 2 in the exponent. And the best, one really nice part, which I should have said with more force, is that we did not mess up anything else when we did that, because we're just plugging in 0. So you can still plug in 0 here and get 1. Putting in the x squared doesn't change that. You can still plug in 0 to the first derivative and still get 1. So what the cool thing here is you can keep tacking on and it doesn't mess up what we've built so far. Okay, I'm going to show you this. So notice the error. Look at the picture on the right. Notice the error. Now I'm going to draw the second Taylor polynomial. Oops, I went too far. Second Taylor polynomial. I'm going to change my numbers a little smaller because it was touchy. First Taylor polynomial, second Taylor polynomial. Look what happens to that error at that particular value. You can see it gets smaller. It starts to hug the graph. And you can see, even if you went on the other side, what happens to the error. In our class, we unfortunately talk a lot about the error. And it looks like the error on the other side doesn't really get that much better. But we're going to keep track of that. Okay, now we're going to keep going. This is where things really accelerate. This is the understanding. So now we're going to take another derivative. This is the rate of change of the concavity, so like the slope of the concavity. So I'm just going to say it tells us more about how the graph curves. So the third derivative is 1. Okay, so I need the third derivative of the polynomial I'm constructing to also be 1. We don't want to mess up anything we've done before, and so we're going to make this an x cubed. So the reason we're making an x cubed is because we don't want to mess up. These other pieces, it's the next simplest term, and I know that if I do 3 derivatives, I want there to be a 1 here. So now let's reverse engineer. The step before, I would like to have an x so that the derivative is 1. But how are we going to make that happen? Because when you take the derivative of this thing, you're going to get a 3x squared. And when you take the derivative again, you're going to get a 3 times 2. The 3 from the step before, and then a 2, x to the first. And that messes everything up. There's an extra 6 we don't want. And that gives you the idea. It's as simple as that. We need a 1/6. Why do we need a 1/6? Because of the 3. Because when you keep taking derivatives, you're eventually going to get a 6, and we don't want that 6 there. So we put a 1 here. The 1 is this number that we want. And that doesn't matter whatever. This works for anything. In this case, all the numbers are 1 that we're putting in these spots. There's a 1 here. There's a 1 there. There's a 1 here. But you're always going to be dividing by 2 to cancel the 2. You're always going to be dividing by 6 to cancel the 3 and the 2. And that will make it match up. And here is that one. So let's look at that error again, but go to the what we call the third Taylor polynomial. That's that. You can see the error on the right has gotten really small, but on the left it's a little bigger, but still it's getting better. Interestingly, it doesn't look that much better yet there. On the other side, it looks way better. You can't even see an error anymore. They look like they're the same function. And the point we're making is it like spreads away from 0 like a disease. Like it just gets closer and closer to hugging this thing. Okay? And basically what we're discovering, what Taylor recognized, is it doesn't matter what the function is. You can just plug in f of 0 here. And then you can plug in f prime of 0 here. And then you can plug in f double prime of 0 here. And then you can plug in f triple prime of 0 here. And it doesn't even have to be 0. It could be some other value. You'd have to recenter things. But that's a story for your actual class. Okay, one more time. Let's go. What's the next one? Again, because we're using e to the x, the fourth derivative is going to be 1. I need the fourth derivative of this to be 1, so I need x to the fourth here. And I want there to be a 1 after 4 derivatives. So the question is, how do I cancel that off? Well, I'm going to have to cancel off a 4. I'm also going to have to cancel off a 3. I'm also going to have to cancel off a 2. And then I want a 1 in that spot. And so at this point, it would be really nice to have a definition. So I'm going to erase all that. So all we're doing is matching up derivatives. Taylor series, Taylor polynomials are a clothesline for hanging out your derivatives. So at any value, here's what we do. You lay out your clothesline, and I'll just give the general formula for a second. Let's pretend we want it based at some other number a. Here's what it's going to look like. And this is the formula. It's just matching up. It's laying out the clothesline, as one of my professors used to say. And then you say, okay, what do we put here? Well, two things. We need to cancel off the exponent. So it's going to look like this. We're going to have, right here, we're going to put 3. 3 factorial. Don't do 2 factorial. 1 factorial. And then this, for some reason, when I search online, there's like tons of videos on what is 0 factorial. But in this situation, we really would like 0 factorial to be 1, just so that we can state our pattern. But that's, again, another thing for another day. And then you put the value of your function. F of a, f prime of a, f double prime of a, f triple prime of a, and you can just keep going forever. Now the forever part is the part where we'd like to prove that the error is getting smaller and smaller. I'm just going to show it to you. So let's keep going. Let's zoom out a little bit. And here we go. It just keeps hugging it. So it gives you a really good approximation really far. That's the 50th Taylor polynomial. So if you were approximating the graph out to like -20, it's going to be really accurate. And it's important we say these things in the right order. It's a good approximation, but it's sometimes going to take a while before it gets good. There's the 100th Taylor polynomial at that point. So you might want to base it somewhere else, and it's fairly easy to base it somewhere else. Like if I wanted to base it at 2, I'm going to change all my x's to x minus 2. And then I'm going to put e to the 2 in all those spots. So now I'm going to show you the Taylor polynomial based at 2. Notice I've shifted it over. And I did that just by putting in a 2 where all those zeros were. And I'm going to be able to get this. So I changed this to a 2, this to a 2, this to a 2. So in all these places, there was an e squared. This is a 2. So it wasn't hard to construct that. And now it's going to be based there. It's going to have a small error around that value. So in practice, usually we base it at 0 if we don't have a reason to base it elsewhere. But if you're approximating the function somewhere else, you'd base it somewhere else and then work from there. It's nice how it does that. You could base it somewhere else. You could say, I'd like to base it at, I don't know, -3. And there's no problem. We can do that. The real value of this is just how general it is. I can pick any value and I can just go and do this and replace the thing with a polynomial. Now I'm based at -2. And it works for any function, and it almost always converges, except there's some important special cases, and you talk about that in that course. That's the idea. The main piece is that we can deal with any function this way, under the right conditions. So e to the x has a nice Taylor series. In fact, I think this is one of the more beautiful things when I first saw this, and my brothers will, if you tell my brothers, they'll make fun of me forever for saying such a thing. I love my brothers, but they don't love math, and they think I'm quite strange for what I do. I like that. It keeps me grounded here. Anyways, e to the x is this. This is way easier to compute. In my mind, this is the best expression for what e to the x is. It's better than writing e to the x because you could actually compute this. You could plug in a 2 here and a 2 here and a 2 here. It's awesome. And if you plug in a 1, you actually get a really nice evaluation of what this is. So that really intrigued me when I was a student. It also just has practical value. Okay, I think I'll end with that. The main concept is that we're matching up height, slope, concavity, and then the third derivative, and then the fourth derivative. We're forming a polynomial. The factorials are there because of the exponents, because we're trying to approximate with a polynomial. It's as simple as that. We need those factorials so that when we take derivatives, the functions match up. That's the conceptual thing. And surprisingly, the more you can get a polynomial to match up at one point, it also matches up nearby surprisingly well. It's really surprising when you see that. Okay, I think I'll end there. It's probably too long. Hope you're listening.